Hey, thanks. Good morning, everybody. All right. Hope everybody's doing well. This is an early class. I don't think I've done 8 o'clock classes much. But thank you to everybody who's here. And let's go ahead and start with any questions, particularly questions on Lab 1, but questions about anything up to this point. All right, well, let me give an answer then to an unasked question. So, Lab 1 and all of the labs going forward, make note that at the end it says for the whole report include cover sheet with your name, class, lab, and completion date. So that's that front page in the beginning of the report. A section named Lessons Learned, which basically summarizes what's your takeaway from this lab. What did you learn in this? And this can be different for every person. So if the lab is supposed to be teaching you how to use Tinkercad, then maybe you came away learning Tinkercad. But be specific in here. For example, if you learned that if you hit Control A and delete, it deletes your entire circuit, right? That's a good thing to put in there. If you learned that it takes longer to do circuits on Tinkercad than you thought, that's something you can put in there, right? This is basically what's the output of having done this lab. What's the benefit to your education? What did you get out of it? So I have a section called Lessons Learned, and then, very important, a section called New Experiment. And this can sometimes be the hardest part of the report to come up with. What we want here is for you to come up with another experiment. So there's 4 experiments in Lab 1. We want you to come up with Experiment 5. And Experiment 5 should be related to what we've covered in the course and gone through in the lab, but it should not be similar to one of the experiments in the lab. So for example, Experiment 2, protoboard connectivity. Okay, cool. A new experiment that would not be acceptable would be, take a large protoboard from Tinkercad and draw the connectivity, because that's basically the same thing as Experiment 2. Or repeat Experiment 3 with a sine wave instead of a square wave. That's not really a new experiment. That's like a variation on Experiment 3. So the goal here is to think about what you did in this lab. What were the different experiments? How are they related to one another? What's the kind of general overall theme of this lab? And then come up with a 5th experiment. And for Lab 1, I'd like you to describe that experiment in sufficient detail that somebody else could do the experiment. So I want more than, Experiment 5. Build a circuit in Tinkercad using resistors, wires, and a battery. That's not very detailed. If I asked you to do that, you would come back to me with a million questions, like what should this circuit do? How many resistors do I need, and so on. So all the detail that's described in here, we want that level of detail, and also what the expected results of the experiment will be. So if you're going to build a circuit and measure the current coming through a resistor, tell me what the reading should be. And for Lab 1, I'm not going to require you to actually perform the experiment, but for Lab 2 on forward, you're also going to have to perform the experiment and write it up as a new experiment. So this can be a significant chunk of time that you spend on the lab, right? Lab 1, you don't have to actually do the experiment, so you just have to think of one and describe it and explain what you expect the result to be. And then Lab 2, you're also going to perform the experiment and then write it up. And I'll save you the trouble and the point loss saying the 4 experiments seemed adequate. I don't think we need a 5th experiment. Does not get you credit, okay? Even if you believe that's true, humor me and go ahead and write up an Experiment 5. All right. So this came up in other places also. For experiment 4, the truth table should have a total of 8 rows, right? Because you have 3 input variables, 3 sensors, 8 combinations, 6 output columns, right? So you're going to have 3 columns for the inputs and then 6 columns, 1 for each of the outputs. So a total of 9 columns in the truth table. And your columns are, red west, red south, red east, green east, or whatever you choose to call them. Green east, east green, I don't care. But your truth table should always contain ones and zeros. And so we can make something like a functional table where the outputs might say, for this combination of inputs, east is green and south and west are red. But that's not a truth table, right? A truth table should have truth values, ones and zeros, in every output spot, every input spot. And
when the light is red, do we also put a 1 for that since it's on technically, or is that considered a 0?
So west, south, east, those are your inputs. We want, green south, red south, green east, red east, green west, red west. Whatever order you like. And then for each of these, ones and zeros, whatever makes sense. But avoid trying to simplify it by having a column labeled south and then writing a G or an R for green or red, or a 1 or a 0 for green or red. I want 6 outputs, right? Because this circuit is going to have 6 LEDs connected to it, and you want to know which signal should I generate to each of these LEDs. Now when you try to write equations for this truth table, you will discover things like, for example, red south is always the opposite of green south. And so maybe, whatever you generate for green south, you'll just run that through an inverter to get red south. That's kosher. But for the sake of the truth table, make sure you have 6 output columns, each with, a total of 8 ones and zeros. So 48 outputs total. All right, cool. Other questions? So I got a few labs turned in already, and they look pretty good. So good job getting those started early.
Do you have an example lab we can look at?
I do not, and that's sort of on purpose. I've debated in the past giving you templates, but I prefer that you actually kind of figure out how you want to write these reports, how you want to organize them, and so on, in a way that makes sense to you, instead of just blindly following, okay, I have to fill in this section, I have to fill in that section. Because I want you to get in the mindset of what is the purpose of this report? What should I put in here, and how should I put things in here to make it fulfill its purpose? And again, its purpose is that if you hand this report to somebody who has nothing to do with Engineering 250, they could reproduce your work, right? They might never have seen this document. They might never have come to class or heard lectures, but just from the report that you've written and turned in, they could do all of the same things that you did, and presumably come up with the same results and conclusions that you came up with. And again, this is how science works, right? Science is about coming up with hypotheses, designing experiments to test those hypotheses, performing the experiments, recording your observations, analyzing your observations, coming up with conclusions. And then that gets, written up, published, other people who have similar backgrounds and expertise review what you did, perform the experiments in their labs, and if 100 people do this and they all come up with the same results, chances are you're onto something. If half the people get different results, then there's something else going on. There's some variable that wasn't controlled or something. And so now, people will start digging deeper in and trying different versions of experiments and so on. And I'll generally give a lot of feedback on lab reports. Not everything that I give you feedback on will cost you points necessarily. Thank you. But you want to make sure you look at the feedback and ask questions about it if it's not clear what I'm saying, because some things that may not cost you points on lab 1 may cost you a few points on lab 2, may cost you half your points on lab 7. So I'll spend some time giving you some feedback on what you turn in. All right, cool. Other questions? All right. So let's continue developing our toolbox of Boolean logic, Boolean algebra, and some of this will still be a review from Engineering CSE 120, but we'll start branching out today into newer material. So we were talking about truth tables, and if we just stick with things with two inputs, A and B, we've got 4 possibilities for our inputs A and B. And if we want to describe some operation, like an OR operation, A or B, we can simply list the value of this function for each set of inputs. And that completely describes what an OR operation does on 2 inputs. It's like a multiplication table in grade school. Since there's only 2 inputs and each input is either a 0 or a 1, we've got, exactly 4 possibilities. And here's what the function produces for each of those 4 possibilities. And so the usual operations we deal with are ORing, ANDing, and these relate to logic, right? As in, human reasoning. This is a 1 if A is a 1 or B is a 1. So here, here, and here are the places where it's a 1. This column is a 1 if A is a 1 and B is a 1, right? Which is only in this lower row down here. An exclusive OR, which is a plus sign with a little circle around it. This should be a 1 if A is 1 or B is a 1, but only A or B, not both of them. And so it looks just like an OR gate, except this last row will be a 0. So it has to be A or B exclusively. One of those can be a 1. All right, so yeah, this is going to be my next question. Is there something particular about the way I wrote this combination of A and B down here? Because every time I write a truth table of 2 variables, you're going to see this exact pattern of 0s and 1s. Is there a particular reason why I might have written it that way? So it is all the combinations, and that's super important because, if we're missing this row right here, we have an incomplete truth table. It's like, hey, what if A is 1 and B is 0? Well, I don't know, it doesn't say. So we definitely want all those combinations. What about the order of these? Any particular reason I might have written it in this order? Ah, so someone said in the first half of the table this column is a 0, and in the second half this column is a 1. And that is significant. So we're going to talk about integers and numbers and how we represent numbers with just ones and zeros, because there's a lot more than two numbers in the world, right? But binary, we only have two values, 0 and 1. So how do we represent, more than two numbers using 0 and 1? So we're going to talk about writing numbers in binary. And it turns out the main way that we're going to do that, this turns out to be the numbers 0, 1, 2, and 3. In other words, I wrote these in a particular order corresponding to how they would represent plain old numbers, integers, in increasing order from 0 up to, in this case, 3. And I'll show you a trick for writing these. So suppose you just have a 1-bit number, right? Just a single bit. There's really only two single-bit numbers, just 0 and 1. So that's easy, right? If someone says, hey, show me all the 1-bit numbers, just write a 0 and a 1. And you could write a 1 followed by a 0, but if you want to put them in order, 0 comes first and then 1. Alright, suppose you want to write 2-bit numbers. Alright, here's the trick. First thing you want to do is copy what you've written so far. So for 1-bit numbers, I wrote down 0 and 1. First thing I'm going to do, I'm going to make a copy of that. And then second thing I'm going to do is for the top half, I'm going to put zeros in the beginning. And for the bottom half, I'm going to put 1s in the beginning. Hey, bingo, there's my 2-bit numbers. Suppose you want to write 3-bit numbers. Well, I'm going to copy what I already had here. 0, 0, 0, 1, 1, 0, 1, 1. And then I'm going to put zeros in front of the numbers in the top. And I'm going to put 1s in front of the numbers on the bottom. Bingo! 3-bit numbers. If I wanted to write 4-bit numbers, I would repeat these 8 numbers down here. I'd put zeros in front of these and 1s in front of these. I would have all possible 4-bit combinations. And I would have them in this way that when I convert these to integers, I get 0, 1, 2, 3, 4, 5, 6, 7. And so this is almost always the way that you'll see truth tables ordered. When you look at a truth table in a data sheet, for example, if it's a function with 3 inputs, you'll see the inputs written in this exact order. Now, is it still technically a truth table if I were to, flip these around or, put this particular row down at the bottom? Technically, yes, it's got the same information in it, but it's not a truth table that people will find as useful as if you put it in this exact order. And writing these in this order, you can use this trick, and you don't have to memorize anything except these two rules, right? Just take the n-bit combinations, write it down twice, put zeros in front of the first half, 1s in front of the second half. Now you've got all the n plus 1-bit combinations. Alright, does that make sense? Alright, so other logic operations, and or are sort of the main two that we deal with. XOR turns out to be useful in some surprising ways, so we'll deal with XORs fairly frequently. But the other thing is we complement these things sometimes. So we'll do A or B, but we'll complement it. So putting a bar on top means take the opposite value. And this is called a NOR. And it's just the opposite of an OR. So instead of 0, 1, 1, 1, this is 1, 0, 0, 0. And then A and B, if we put a bar on that, we get an AND. And it's the opposite of an AND. So instead of 0, 0, 0, 1, we get 1, 1, 1, 0. And if we do an A XOR B with a bar on top, that's the opposite of the XOR. That's called an XNOR. And instead of 0, 1, 1, 0, we get 1, 0, 0, 1. And I probably should have started with a simpler truth table, which is just a function of a single variable. And the main thing we do if we have a single variable is we can negate it. And this is called not. And it's just the opposite of the input value. Alright, so why do we care about this? These are kind of the building blocks of more complex circuitry. Sometimes, you know, you want to build a circuit that tells me, hey, is this input a 1 or is that input a 1? Well, that's easy, just use an OR gate. But more often, you know, you want to build a circuit which says, hey, you know, if there's a car present to the south and no car on the east, we want the south light to be green, we want the other lights to be red. And we're going to have to take some combination of logic gates and put them together in certain ways to create something whose truth table corresponds to that description. And so these are building blocks, and everything we do in this quarter, we're going to learn building blocks first, and then we're going to learn ways to put those together. And sometimes there's very mechanical ways to do this. Sometimes it's a matter of practice and, you know, intuition and experience to know how to put things together. Most of what we do in this course will be pretty mechanical. If you have a truth table, we'll have very sort of, you know, turn the crank algorithms for coming up with equations and then circuits and then simplifying them. But we still need this really solid understanding of what's going on. So a general approach we'll take is to, you know, take a description of a problem, and from there we'll come up with a truth table. And from the truth table we'll try to come up with equations. And equations are, you know, combinations of ands and ors and nots and so on and so forth. So let's go back to that combination lock example that we started on Monday. And so we were building a circuit. It had 3 inputs, probably push buttons, and it had an output called unlock. And the meaning of the 1s and 0s here was if the unlock signal is a 1, then the thing that's being controlled is open. And if the unlock is a 0, then it's locked. And for these, we're going to say if this is a 1, then that corresponding button is being pushed down. If it's a 0, then it's not pushed down. And so certain combinations of pushing certain buttons should unlock the thing being controlled by this. So when I write truth tables with more than 2 variables, I tend to break them into chunks of 4. And so this line here is just a dividing line just to help keep things organized so it's easy to know, what's the output corresponding to this row, for example. And so I gave you my secret password, which was 111. That's going to unlock my output. And all other combinations are going to leave the system locked. And so our equation for this truth table was just to use an AND gate. Right? Take A, and B, and C. And by the way, when you write AND gates, right, you can put a dot in between them, or you can just write them next to each other, and it'll be assumed that there's a dot there and you're multiplying. Just like with, algebra. So A dot B would be the same thing as just AB. The dot can make it clearer sometimes. And then there was the twist of, suppose you want to give your friend access to whatever this unlocks, but you want to give them their own special secret code. So I don't remember what we did last time. Let's just suppose we're going to give them the code 011, so we're going to put a 1 in here. So now we want to unlock if A is 1 and B is 1 and C is 1, right? Or if A is 0, B is 1, and C is 1. Well, we don't have a logic gate for... Oh yeah, it was the cookie recipe. Thanks. We don't have a logic gate that, outputs a 1 when A is 0, B is 1, C is 1. We do have a logic gate that outputs a 1 when all three of the inputs are 1. And so what I'm going to do is, instead of saying I want A to be 0, I'm going to say I want the complement of A to be 1. That's exactly the same thing. Right? Saying I want A to be 0 is the same as saying I want A bar to be a 1. So now I can say I want to unlock my box when A and B and C are 1, or when A bar and B and C are 1. Well, how do I tell if three things are 1? I'm just going to AND them together. So A bar and B and C will be 1 exactly in this case. So now I can write my nice Boolean formula, unlock equals A, B, C, or A bar, B, C. And that corresponds to this truth table. And if I have a third friend who I've decided to trust with my secret recipe, and I'm going to give them the combination 1, 0, 0, well, I can extend my logic here and say, hey, I also want to unlock if what? A is a 1, and B is a 0, in other words, B bar is a 1, and C is a 0, in other words, C bar is a 1. And so this equation will correspond exactly to this truth table. Alright, so we're going to come back in a little bit and we're going to talk about a sort of methodical way to do this without having to think through, A equals 0, A bar equals 1, and so on. We'll find an algorithm for writing this down directly just by looking at that truth table. Seeing the output values, we'll be able to write these without too much work. So any questions up to here? Alright, so we've got an equation. Let's sketch out a circuit that will implement this equation. And so to make a circuit, we need to have symbols that we use for these basic operations. And so what's the symbol for a NOT operation? Do you remember this? So it's a bar on top of a variable. What if I'm drawing a circuit diagram? It's a little circle, and it's usually a triangle with a little circle on the output, but technically it's the little circle that means not. Cool. All right, so an OR gate is like this kind of funny stretched out half moon shape. And an AND gate is this semicircle like that. And these can be confusing, especially in the heat of battle when you're sketching things quickly. So here's something I do when I write OR gates or AND gates. For an OR gate, I put a little plus sign inside, and for an AND gate, I just put a little dot. And now, you know, if my vertical bar here starts to get a little sloppy and it starts to look like this, it's still clear this is an AND, because there's no plus sign. And if my curve in the beginning of this symbol isn't quite as curved as I'd like it to be, and it starts to look like this, I still know this is an OR gate, because there's a little plus in there. And then XORs look like OR gates, but they have an extra thing in the beginning. And I'll still put a plus in there, or maybe a plus in a circle. And so these are just pictures we use to represent these operations. And a NOR looks exactly like an OR, but there's a little bubble on the outside. Again, the little circle basically means not. And a NAND, I'll just draw an AND gate and I'll put a little circle on the output side. And an XNOR, I'll draw an XOR. And I'll put a little bubble on the output. And so those are pretty standard symbols. But these bubbles can take on a life of their own. And for example, you might see something like this. Do it like this. Right, this is like an AND gate, but there's a bubble right here on the input. Well, this is a piece of logic that does the following. It takes A, it negates it, and it ends it with B. And we don't usually go into our parts bin and find, you know, a half AND gate or something that we might call this, right? But you'll see things like this in circuit diagrams. And if I wanted to build this, maybe I would take an inverter, run A through the inverter, and then feed that with B into a gate. And you'll also see, you know, things like this. This is a 3-input AND gate. So it takes these 3 inputs, ANDs them all together, and gives you an output. So what does the AND of 3 inputs look like? What do the 1s and 0s look like in this output column? This is a 3-input AND gate. And if you don't know, think about the logic. All 0 except the last row. So the logic that this is saying is I want an output to be 1 when A is 1 and B is 1 and C is 1. That only happens right down here. And in all these other cases, it's not true that A is 1 and B is 1 and C is 1. A is 1 and C is 1, but B is not 1. So the AND is a 0. How about the OR of A, B, and C? A or B or C. You can shout in your microphone if you want. These are all 1 except for the first row. Because this says the output should be 1 if A is 1, or B is 1, or C is 1. Well, in all of these 7 rows, at least one of A, B, or C is 1. But in this first row, right, is A 1? No. Is B 1? No. Is C 1? No. This is a 0. But all the other cases, the output is a 1. And so a NAND would be all 1s with a 0 down here. A NOR would be a single 1 with 0s down here, and so on. Alright, so let's build a circuit for this. So we want ABC or A bar, BC, or AB bar, C bar. Well, we can start trying to sketch this out. Let me show you a not very good way to draw this circuit, and then let me show you an excellent way to draw this circuit. The not very good way, which is still technically correct, is you know, I've got A, B, and C. Those are my inputs. Well, I want to run those all into an AND gate. So that's one output. Then I want to take A and run it through an inverter. And I want to take B and C. And I want to put those through an AND gate. And I want to OR those. And then I want to take A and I want to take B bar and I want to take C bar and put those through an AND gate and then put that through an OR gate, and there's my output. And so you can do this, and technically it's correct. But it's a little hard to know what's going on here. If you just look at the circuit diagram, it would take some effort to figure out what the equation is. And more importantly, if there's a problem in this diagram, it's going to be tricky to find. And so if you take this diagram and you build it into a circuit, and your circuit doesn't quite work the way you wanted it to, it starts unlocking with this instead of that, right? Then is there a problem with the diagram? Is there a problem with the way I built it? You know, it's going to take some work. So let me show you a cleaner way to sketch a circuit. Alright, so you're going to work with this equation. So this will always work for you, and this is what I recommend doing anytime that you have to sketch a circuit. Take your inputs, put them over here on the left, and just run some vertical lines. Alright, there's all of our inputs. And then on each of these inputs, run it through an inverter, make another vertical line. So now I've got A coming along this line. I have the inverse of A bar, coming down here. I have B and B bar, I have C, and I have C bar. And now let's make the pieces of our equation. Our first piece is A ANDed with B ANDed with C. So I need a 3-input AND gate. So I'll put one right here. And the 3 inputs I want to AND are A. So I'm going to draw a wire from here to A. B, so I'll draw a wire from here to B. And C, I'll draw a wire from here to C. So this output is A and B and C. We need another 3-input AND gate. And this should AND A bar, B, and C. So I'll draw a wire from an input over to A bar, another to B, and another to C. This is A bar and B and C. That's this term. And the third one is A ANDed with B bar, ANDed with C. So another 3-input AND gate. The first input should be A. Second input should be B bar, which is this line here. Third input is C bar, which is this line here. There's A, B bar, C. And now I want to take the OR of each of those. So I'll take those, run those through a big OR gate. There's my unlock signal. And no matter how complex my equation is, no matter how many inputs I have, how many terms I have up here, I can always use that approach to draw a circuit diagram. And a diagram like this I can turn into a protoboard circuit, a physical circuit, or a simulated one in Tinkercad pretty easily. And I can use this diagram to debug the circuit that I build. If I build a circuit and I say, you know, if I put in a 1, 0, 0, my output should be a 1, and that's not what's happening, I can use this diagram to find out where the problem is. We'll dig into that when we start building circuits in some future labs. So this is one way to go from an equation to a diagram. And it always works. And if you want, you know, you can do this in pencil. You can get rid of these stray lines down here. I never used, well, I did use C-bar. But, you know, you can clean up the diagram if you want, or you can just leave it like this. And we'll actually come back and revisit this in a few weeks when we talk about programmable logic and gate arrays. And this will figure prominently in that future topic. All right, good so far? All right, so if we were trying to build, you know, this thing for controlling this box, we would start with the description of the problem. We would go from there to a truth table, right, which says, you know, we should unlock in these situations. We would go from that truth table to an equation, from the equation to a circuit diagram, and then from the circuit diagram we would try to implement a physical piece of hardware. Alright, so what does that look like? So there's, you know, an example of a physical circuit. It doesn't help. So that's really washed out. Each of these dark things on top is an integrated circuit. If you're in person in your lab courses, you work with these physical devices, these ICs that let me pop one out for you. That look like this. So there's these little plastic packages with a bunch of pins coming out the side, and some really hard to read writing on top that I'm not even going to try to show you on here. but a description on top that says, among other things, what type of device this is. And so there's a part number, and there's date codes and who manufactured it and all this kind of stuff. And this board that I built last summer has these little sockets that you can put these chips into. And then you use solder and wires to connect different pins of different chips together, and you get some kind of behavior out of that. This is a hard drive controller that I designed and cobbled together. In Tinkercad, right, we use a protoboard, that white board with all the holes in it, and we drop these chips in there, and we can plug wires into holes and make these wiring connections without having to use solder, without having to melt metal and make these things permanent. And so we can change our connections easily, and so on and so forth. And these integrated circuits, these packages, are physical devices that perform things like logic operations, that do things like, a logical or logical and. So how do you work with these things? Well, these physical devices, they come with something called a data sheet. And every physical device that you're going to work with, there's a data sheet corresponding to it. And you can find data sheets on the website for this course. So ENGR250.com is the main website for the department. If it asks you for a password, the password is Clark, just lowercase, C-L-A-R-K. So I can come over here to component specifications and find a bunch of different types of chips. For example, a 2-input AND gate. This is a device called a 74LSOH. And you can find one of these little 14-pin packages, and written on the top will be 74LS0H. And if we click on this, we can come to a data sheet. And so let me show you a different data sheet for 74LSOH. And so part of doing engineering is getting really good at working with data sheets, because these are everything you need to know about these physical devices. Now, mostly all you need to know is that it takes in 2 inputs, it gives you the AND. But how do you hook it up? How do you power it? How much output can you get from one of the outputs? What are the characteristics of the inputs that make an input a 0 or a 1? What temperature can you work this under? What's the physical dimensions of it? All of that information is inside the data sheet. So let's just look at a typical data sheet here. This is for positive AND gate, and it says quadruple 2-input positive AND gate. There are 4 AND gates inside this one chip. Why? Because, having a chip with 3 pins on it wouldn't be terribly useful. 14 pins is typically a small device, and if you got 14 pins, that's enough to fit 4 AND gates. So you get 4 for 1. Alright, so here's the different part numbers for this. There's a description of it. This was from December 83, revised in March 88, if anybody is interested. Packet options include, there are different versions of this chip, different physical forms of this chip. Here's the one that we would use in lab. It's called a dual inline package, or a DIP. It's got 2 sets of pins side by side. But here's a different package we could get. Right, this is a flat pack. It's got a total of 20 pins on each of the 4 sides, but they're not pins that are sticking out. We can't use this with a protoboard. This is a low-profile device that's useful for soldering onto a circuit board. So different package options. Dependable Texas Instruments quality and reliability. Well, that's a marketing thing. The manufacturer of this chip is Texas Instruments. And so, you know, putting a little pitch in here for dependable, you know, and quality and reliability. It's sales. All right, description. These contain 4 independent 2-input AND gates. The 54 versions, those are mil-spec. They work over a wide temperature range, negative 55 Celsius to 125 Celsius. You can put this in your boiling tea water and not destroy it. The commercial devices start with a 74. Those work from 0 to 70 Celsius. And then here's a function table, or a truth table, right? So 2 inputs A and B. If they're both high, so here they're using high and low to represent 1 and 0. This is pretty standard. If they're both high, the output is a high, because it's an AND gate. If input A is low and input B is an X, well, X is a wild card. It means X can be anything. If A is low, the output's low. And if B is low, A can be anything, the output is low. So they were a little lazy. They didn't want to write all 4 rows of the truth table, so they used some wildcards in here. And they violated my principle. They wrote the 1.1 version first, and then the other versions after that. So they didn't put them in the same order that other places might. Now this data sheet from the website, right? It's still a 74 LS08, but this is by National Semiconductor, different company, right? And their truth table, 00011011, right? So that's that standard order. And the output is low in all cases except when both inputs are high, and then it's a 1. And they put a little key down here. H means a high logic level, L means a low logic level. So H is a 1, L is a 0. And they also put a little equation up here, y equals AB, to say, hey, this is a logical AND operation. All right, logically, we can think of this device as having 8 inputs. These are inputs 1A and 1B, and this output is called 1Y. And the presumption here is, you know, Y is the AND of A and B. And then here's a logic diagram which shows you explicitly Y is the output of an AND gate whose inputs are A and B. 1AB gives you 1Y, 2AB gives you 2Y, and so on. So if we go back to this picture of the chip, and these chips have this little notch on one end, if we look at the top of the chip and we put the notch right here, then this pin 1 is 1A, this is 1B, this is 1Y. And so physically, if I put a pair of 1s into these 2 pins, I should get a 1 coming out of this. And if I put, say, a 1 and a 0, or a 0, 1, or a 0, 0, I'll get a 0 out of pin 3. And so this is a physical implementation of that logic gate. So what does it mean physically to say that I'm going to put in a logic 1 or a logic 0? How do we do that with an actual physical circuit? Think back to like ECS 120.
You give it an input.
What sort of input? You're right. So it's in chat, high and low voltage. So these devices are voltage sensitive. And do you remember what voltage level corresponds to a 1? Actually, you might not, because you probably did 120 in Tinkercad, I'm thinking. So positive 5 volts is a logic 1, 0 volts is a logic 0, roughly speaking. So if I were to take a 5-volt battery and connect it to this pin and this pin, and then measure the voltage coming out of here, I would read 5 volts. And if I put a 5-volt battery on pin 1, but I connect pin 2 to ground, which is 0 volts, then my output pin 3 would be 0. Alright, here's what's going on inside. If you didn't have this chip, this is what you would have to build to make an AND gate. You'd have transistors and resistors and diodes and wires, and depending on whether it's a 7408, LS08, or S08, different circuit diagrams. But a big mess in any case. Right? So 74LS08 has 4 copies of this circuit inside this one little chip. And these are one of the things that kind of revolutionized the world as far as technology. Alright, absolute maximum ratings. Right? These things, these chips need power. So this is another thing. Actually, you do have to do this in Tinkercad. So in order for this chip to do all these things that we're talking about, you have to power the chip itself. You have to plug it in. And you plug it in by connecting pin 7 to 0 volts or ground, and pin 14 to what's called VCC. That's typically 5 volts. And after you've done that, 5 volts here, 0 volts here, then you can feed in inputs to pins 1 and 2 and get the AND of those on pin 3. Or feed inputs to 4 and 5 and get the AND of those on pin 6. So you typically power it with 5 volts. The most you can power it with is 7. If you go above that, it's probably going to smoke. The most you can put into your inputs, remember your inputs are supposed to be 5 volts for a logic 1, you can go up to 5.5 volts, maybe 7 volts, depending on which type of chip you're using. If you go beyond that, things are going to smoke. And then there's operating temperatures and storage temperatures. And then there's the recommended operating conditions. Well, they recommend the supply voltage is between 4.5 and 5.5, typically 5 volts. That's for mil spec. For the commercial ones, 4.75 to 5.25. So pretty precise. If I try to power this with 6 volts, it's probably going to degrade the chip. It may fail at some point. Alright, if I want to input a logic 1, a high level input voltage, I should feed it at least 2 volts. Now we said over here 5 volts is a logic 1, but apparently anything from 2 volts to 5 volts will be a logic 1. And if I want to input a logic 0 low level input voltage, it should be less than 0.8. The maximum I can put in for a low level is 0.8. So I don't have to get all the way down to 0 volts. I can go up to 0.8. So 0 volts to 0.8 volts will be a logic 0, and 2 volts to 5 volts will be a logic 1. So what if I put in an input between 0.8 and 2 volts? Is that going to be a logic 1 or a logic 0? This is a critical question. Someone said, I'm guessing 0. Someone said it won't register on either. The answer is we don't know. So here's what the data sheet is telling us. If we put in at least 2 volts, all the way up to actually, 5.5 volts. Anything in here, this is a logic 1. And if we put in anything from 0.8 volts down to 0 volts, this is a logic 0. But this section in between, all bets are off. If we put in 0.9 volts, it will probably register as a logic 0. And if we put in 1.9, it will probably register as 1, but it's not guaranteed. It could be both. It could flip back and forth. It might register as a 0, and then the sun comes out and shines on my circuit, and all of a sudden that input becomes a logic 1. So this is digitizing. This is the whole transition from analog to digital. This is what it means to be talking about digital logic. We've taken this input range, which could be anything from 0 volts to 5 volts, and we've broken it into 2 buckets. There's the bucket up here, which is high, which is true, which is 1, which is on. And there's the bucket down here, 0, off. And we have this forbidden range in the middle that we're not supposed to use. We should never have an input voltage in these regions. And so the way we can take our analog voltage, our thing that changes continuously between 0 and 5 volts, and treat that digitally is to say, hey, we're going to break this into 2 buckets. And we don't want, a razor's edge between one bucket and another. We want a dead zone in there. So we can say, hey, down here, that's a 0. Up here, that's a 1. And the stuff in the middle, hey, we're not supposed to have things in that range. And that's okay, because the output voltages will be set up in such a way that we the output for a high, right, will be at least 2.4. So when the output of a chip is trying to say, hey, logic 1, it's telling us it's going to be at least 2.4. Well, that's, something sitting up here. And so the output of a chip will be somewhere safely inside this 1 region. And if a chip is trying to output a logic 0, this tells us the low-level output voltage will be no more than 0.4. And typically 0.2. So right down here, 0.4. This is where it's going to output a 0. This is where it's going to output a 1. This is what makes computers work. The fact that we take this input voltage, which is, just a voltage, could be anything from 0 to 5, could be, 3.72 volts. And we just kind of like round that up and say, hey, we're going to treat that the same as 5 volts. Or, 0.6, we're going to treat that as 0 volts. And these devices are made so that when they want to output a 1, they output something that's clearly going to round up to 5 or round down to 0. And so we can take the output of one of these gates and feed it to the input of another gate and know that that other gate's going to treat the input the way that we wanted it treated. Alright, switching characteristics. TPLH, we'll talk about these a lot in about 3 weeks. This is how long it takes this circuit to do the thing it's supposed to do. So what is an AND gate supposed to do? If both inputs are a 1, the output should be a 1. So suppose my inputs are 1, 0, my output's a 0. And suppose B changes from a 0 to a 1, my output should change from a 0 to a 1 also, right? But does that happen immediately? No. Very few things in the universe happen immediately. So at the point where B changes from a 0 to a 1, where its voltage goes above this threshold, my output will still be a 0 for a little bit of time. because, you know, all that circuitry inside the chip, those transistors and resistors and so on, need to be able to respond to that input. So how long does it take? Well, there's a propagation delay. So the propagation delay from an input change to an output change going from low to high is typically 17.5 nanoseconds. No worse than 27. And to go from a high to a low, that's a little quicker. It's typically 12, no worse than 19. And all of these chips have some kind of propagation delay. Some time it takes for an input change to propagate to the output. So question, how long is a nanosecond? Any ideas? Or what does the prefix nano mean? It's very small, definitely. 10 to the minus ninth, there we go. So a nanosecond is a billionth of a second. All right, 10 to the minus ninth seconds, so... I think it's that. So a millisecond is a thousandth of a second, a microsecond is a millionth, a nanosecond is a billionth. So if something takes a nanosecond, that thing could happen a billion times in 1 second. Which sounds pretty fast. But if something happens in a billionth of a second, that means it happens a billion times per second. Well, that's what we would call a gigahertz. If something was changing a billion times a second, it would be oscillating at a frequency of a gigahertz. Which, you know, for a modern computer is kind of pokey. Most computers are, you know, 1 point something, 2 point something gigahertz. That's for 1 nanosecond. Well, if this thing took 10 nanoseconds to switch from high to low, that's a tenth of a gigahertz. That's 100 megahertz. If it takes 20 nanoseconds, we're down to 50 megahertz. Is 50 megahertz fast for a computer? Probably not. I think my first computer might have been 50 megahertz. Actually, my first one was 1 megahertz. But by today's standards, this is slow. You would not want a computer where a single AND gate could run at a maximum of 50 megahertz. That would be like really, really slow. So even though these chips are pretty cool and pretty powerful and so on, right, they're not particularly fast. Now, we don't care about this because, you know, if we're building our traffic control circuit and a car shows up, we don't need the light to change in, you know, 1 nanosecond. So these work fine for the kinds of things we're going to do where we're basically working at like human speeds. But if we were building a computer, we would not want to use these chips. It would be a really slow computer. And we'll play a lot with propagation delays in a few weeks when we start talking about circuits that have memory. So switching circuits, things like that. All right, and then there's more and more information in this data sheet. So different packages that you can get, whether they're active or obsolete, the type of and the number of pins, and so on and so forth. and different data sheets from different manufacturers, different information that you'll find in different formats. If you were to order a bunch of these and order them in a form that comes on a big strip of tape, right? Well, here's the information you would have, right? How big is the plastic reel that these things come on? How far apart are these on the tape? How far apart are the sprocket holes, and so on? Thank you. Right? Why do we care about this? Because most people don't sit around and put chips into proto boards. If you're trying to build, you know, 1 million boards, you have machines build these. And the machines are called pick and place machines. You basically get a bunch of these chips on a plastic reel. You put this reel on a machine, and something runs it through, just like a movie film, right? There's sprockets that move the film into precise positions, and then mechanical arms that come in and pull these chips off of this tape, and we'll place them onto a circuit board to be assembled. And so here's, you know, the circuit board that I showed you that was, you know, built by putting wires through little holes and soldering them on the back. And that's a very kind of manually intensive process. Here's a circuit board made with different kinds of chips that that have a very low profile. This is really horrible lighting. How can I get that less? Maybe I can do this. There we go. That works better. So these are like the integrated circuits that you would use in your lab, except they're flat packs. They don't stick up very far, and they come off, you know, typically a tape, and they get put on a circuit board and then soldered into place. And this can be done by machine. This I did by hand. But there's machines that will do this and produce, you know, large numbers of these. And go find some YouTube videos on pick and place machines. They're fun to watch. Kind of mesmerizing. So if you're going to do that, you need this information, right? What's the real diameter? What's the spacing between the chips, and so on and so forth? What's the box that it comes in, right? Because maybe you don't want to open this box yourself. Maybe you're going to have a machine that opens the box for you. So you want to know the dimensions of it, and so on and so forth. And then detailed drawings of the chips themselves, the spacings, and so on and so forth. When you're designing a circuit board like this, you need to know, you know, where should I put the little metal contacts that the chips are going to get soldered to. And so depending on how you're going to use these devices, you might need, you know, some or all of this information. Those physical dip chips, the things with the leads coming off the bottom, well, here's all the information on those. How far apart are the leads, which is typically 1/100 of an inch. What angle does that bottom part of the pin, let's go to the dip, there's a dip chip, right? These don't come straight down, they come out at an angle. And so all this information is available in the data sheet. Mostly for us, for what we're going to be doing, all we really care about is sort of the functional behavior. But depending on what you're doing in the future, right, you may need more of this information. And then there's usually a disclaimer at the end which says, you know, don't use this for nuclear applications, don't use it for life critical applications, and so on and so forth. So for an AND gate, we can get away with probably just this first page. That's pretty much everything we need. Now, Engineering 270, if you're taking that in summer, you might take it with me. We mostly work with one chip in there. It's called the PIC 18F1220. The data sheet for that chip is over 300 pages. And we'll spend a good part of the course just working with that one data sheet and learning different sections from it. So this is probably the most important skill you can come away with from a course like Engineering 250, is knowing how to get through a data sheet. Even though we don't need to get terribly deep into them for this course, down the road, especially if you're working as an engineer, this will be your go-to. This is how you work with a new device. This is how you answer all the questions about what does this do, how do I use it, and so on. All right, and again, you can find those on ENGR250.com. Click through where it says component specifications, and if it wants a password from you, it's just lowercase Clark. That's just to keep the robots out. There's some pictures I took before of some of these chips. So there's the dip chips that we use. Here's a low profile, small outline integrated circuit. So it's the same layout as these dips, but it's smaller. The pins are closer together. It's not as wide, and it doesn't stick up as high. Here's a quad flat pack. So we have pins coming out on all four sides. So we can have more pins in a smaller form factor. Here's a quad no lead flat pack. So the contact points are just these little pieces of metal around here. And this just sits, upside down on a circuit board and gets soldered into place. And you usually make this solder connection not with a soldering iron, but with something like a toaster oven. You heat it up and the solder melts and it adheres to the circuit board. And this was a chip that I took apart. I bought it from Amazon cheap, and it wasn't working for me. And I was curious if it was actually the chip that it said it was. So I pulled it apart, and this was what was inside. And it's just a little maze of mosaic patterns. But these are wires and semiconducting materials that act like resistors or transistors or conductors and correspond to those circuit diagrams that you see. And yeah, I was able to confirm this actually was the right chip. I was just using it wrong. All right, so that's plenty for now as far as the hardware side of this business. Questions about any of that? All right, let's do like a 4-minute break. Let's come back at 9:22. I have lab hours today from 5 to 8 p.m. and those are just for this class, so it won't be students coming in for advising and stuff. So yeah, come by 5 to 8 p.m. For office hours if you like. All right, so yeah, let me mention lab hours. So additional course policies. So I'll be available in the regular Zoom classroom Wednesday evenings, 5 to 8 p.m. for lab questions or homework questions or whatever. But those are engineering 250 hours. So that's going to be in the same Zoom room that you're in right now. My office hours that are on ENGR250.com, those are a separate Zoom room, and you can find the link for that on ENGR250.com. And that's Tuesday, Thursday, and Friday mornings. So you're welcome to any or all of those hours. All right, let's talk a little Boolean algebra. So if we think of things like A, B, C as being Boolean variables, true or false, 1 or 0, high, low, etc., and we have these operations like and, or, not, and so on, and we have these symbols that we use, so we can put a bar over something for not, we can put things next to each other for and, we can use a plus for or, and so on. We can start to talk about an algebra, a mathematical system involving Boolean operations on Boolean variables. And in this algebra, we find some properties that are familiar to us, and some that may be novel. For example, A or B is the same thing as B or A. This is called commutativity. And similarly, A and B is the same thing as B and A. That's also commutative. Well, what does this mean physically? It means if I have a chip and I'm told that the output is the AND of pin 1 and pin 2, and I want to AND A and B, I could put A to pin 1 and B to pin 2, or I could put B to pin 1 and A to pin 2. Doesn't change the output. So I can swap around which inputs I'm connecting, and I get the same behavior. Well, that's useful to know. I can move the parentheses around. If I take B, C, and I OR those together, and then I OR the result of that with A, it's the same thing as taking A, B, ORing those, taking that result and ORing it with C. And since the parentheses don't matter, we sometimes would write either of these as just this. And this is called associativity, or the associative property. Well, this is really useful to us when we build circuits, because what is this thing over here? This is a 3-input OR gate. But what is this thing? This is an OR gate that takes B, C, and ORs those together, and then ORs that with A. And this is a circuit that takes A, B, ORs those together, and then takes C and ORs that with the output of A or B. And associativity tells us that this and this and this will all be the same value. Well, one thing that means is if we don't have a 3-input OR gate in our parts box, but we have a couple of 2-input OR gates, we can get the same behavior of a 3-input OR gate using a pair of 2 inputs. And the same thing happens for ANDs. And so this could just be written as A and B and C. So commutativity, associativity, and these, you know, are the same things that we find with plain old numbers when we talk about algebra. 2 times 3 is the same as 3 times 2. So that works for Boolean algebra. We also have what we call double negation. If I take A and I invert it and I invert that again, I get the same thing as A. So what does that mean? If I take A and I put it through a pair of inverters, I'm going to get A out the other side. Alright, anybody recognize this? It's got a name.
Is it a redundancy?
Not exactly. It's named after someone. So this is deMorgan's theorem. And it tells us that if we want to take an OR and negate the output, we have the option of negating the 2 inputs and then ANDing them. And there's 2 versions of this. The other version says that A ANDed with B negated is the same as taking the negated inputs and ORing them. And from this we can also see the following. These 2 things are not the same. If we take A, B, and we negate those and we AND them, it's not the same thing as taking A and B and negating the output. We will get different results. And so when you're writing up homeworks or labs or exams, if you want to write A bar, B bar, I strongly recommend using parentheses. Because, you know, A bar, B bar, sometimes your bars get close to each other, and sometimes they start to look like a single bar. And if I see this and I wanted to see that, right, then it's not the right answer. So even if your bars get really close to each other, if you put them in parentheses, it makes it really clear. Negate this, negate that, and then put the AND of those together, right? That's this thing up here, which is the same as this. So what does this mean? If you take A, B, and you put them through an OR gate, and then you complement the output, or if you take A, put it through an inverter, take B, put it through an inverter, and then put those through an AND gate, you got the same output here. Exactly the same value. And so just because engineers can be kind of quirky sometimes you'll see a circuit like this. Guess what? This is an OR gate. It's a different way of drawing an OR gate. But what it's actually saying is I want to take A, complement it. I want to take B, complement it, and then I want to AND those two complements. In other words, I want to do this operation. Oh, I forgot my bubble out here. And then I want to put a bubble on the outside. Well, A bar ANDed with B bar is a NOR gate, and then if I put a bubble on the output, that gives me an OR gate. So this is a bizarre way of writing A or B. And you can work through it logically, right? If both of these are 0, then both of these inverted inputs will be 1. Your AND gate will output a 1. This will output a 0. But if any input or both inputs is a 1, it will get complemented to a 0. Your OR gate will output a 0, and when you invert, you'll get a 1. So this is a bona fide OR gate. But for various reasons, sometimes we like to work with these bubbles and think about, you know, inverted inputs, inverted output. The other thing this tells us is that if we're trying to build a circuit and we don't happen to have any OR gates, but we have some inverters and some AND gates, we can get an OR behavior by using deMorgan's theorem. So deMorgan's theorem is super powerful. All right, and then we get a whole bunch of identities, and you can find these in the textbook, but let me just give you a few examples of these. If I take A and I AND it with 0, I get 0. If I take A and I AND it with 1, I get A. If I take A and I OR it with 1, I get 1. If I take A and I OR it with 0, I get A. If I take A and A, I get A. If I take A or A, I get A. If I take A and A bar, I get 0. If I take A or A bar, I get 1. And there's a whole slew of these things we can do. And there's some parallels between what I've written here and what I've written here. I've put things in the same form on the left here. But there's a pair of A's, there's a 0 or a 1. There's a pair of A's, there's a 0 or a 1. And this gets into something that we can call duals. And duals are everywhere in our world. And what happens is we can start developing a whole theory around AND operations. And as we develop this theory, guess what? We're also developing a parallel theory about OR operations. Or we could, you know, just think about OR gates and start developing some facts about OR operations. And at the same time, we're also developing a series of facts about AND operations. This is very much like voltage and current. This is very much like KVL, KCL. As soon as you discover Kirchhoff's current law, you're right on the cusp of Kirchhoff's voltage law, because they're really the same thing. It depends if you're looking at current or voltage. It depends if you're multiplying by resistance or dividing by resistance. And so throughout computer science, electrical engineering, philosophy, religion, all these different fields, we always find duals. And duals exist because, as humans, we tend to try to break things into buckets, I believe. And we take one thing and we break it into two buckets. But these are really the same thing. ANDs and ORs are really the same thing, right? They're connected through this magical thing called deMorgan's theorem. And so this is going to come up a lot, especially if you're computer science. We're going to see all of these things again and again throughout different CS courses we'll encounter this idea of dual operations between ands and ors. It'll pop up in set theory. It'll pop up in programming languages. It'll pop up in function theory. All kinds of different contexts. So you can look in the text. You can see a couple of pages of these identities and these algebraic properties of commutativity, associativity, and so on. And we'll come back and use these in various ways as we continue developing techniques for going from truth tables to equations to circuits. Alright, let's switch gears and talk about numbers, because this will be a big chunk of the homework, and then we're going to talk about the homework. So, there are lots of numbers in the world, right? There's a 5, and there's a 7, and there's a 3, and there's a 26, and so on. And binary, we've got two things, 0 and 1. So we have to use combinations of these bits, these binary digits, to represent, you know, more than two things. And we could do this, you know, a variety of ways. I could just say, okay, 5 is my favorite number, so I'm going to use, you know, this to represent this number, and I'm going to use this to represent this number, and I don't like the number 3, so I'm going to use that to represent the number 3 so that people don't write it, and I'm going to use this to represent the number 26. We could just make some arbitrary assignment of bit patterns and numbers, and that's totally legal, but not terribly useful. Alright, has anybody ever seen this number before? It's a new number I just came up with. I'm guessing nobody has encountered this number before. It's not anybody's, you know, bank account balance or, you know, address of their house or favorite number or anything like that, right? It's probably a number nobody has ever seen written before. But every one of us knows what this number is, right? I mean, we could count it out. It's 1,243,659,227. Oh, and it's someone's cookie password. Awesome. So we know what this number is. If I asked you to add 1 to this, everybody would be able to do it. If I asked you to divide this by 10, everybody would be able to do that, right? Why is it that I can write an arbitrary collection of symbols and everybody knows what that represents? Because there's a pattern, right? And the pattern is very straightforward. This is the ones place, this is the tens place, this is the hundreds place, this is the thousands place, this is the 10,000th place, and so on. And so this number represents 7 plus 2 times 10 plus 2 times 10 squared plus 9 times 10 cubed, and so on. It's not an arbitrary mapping from symbols to numbers. It's what we call weighted positional notation. Each position corresponds to another power of 10, and we multiply that power of 10 by the digit we find in that position. And so if we do all of these operations, we end up with a number, 1,243,000,000, etc., right? And that's the number all of us would come up with. And then if we want to add 1, well, you know, we just add a 1 to the ones place, we change that 7 to an 8, there's no carry, we're done. But if I use this representation for my digits and I say, what's 5 plus 7? I don't know. I mean, how do you write 12? So weighted positional notation is why arithmetic works. And so we're going to carry that over to binary, and we're going to use weighted positional notation for our binary numbers. So here's a binary number. What does that number represent? Weighted positional notation. So this is the ones place, this is the 2's, this is the 4's, this is the 8's, this is the 16th. This is 2 to the 0, 2 to the 1, 2 squared, 2 cubed, 2 to the 4th. So this is the number 1 times 1 plus 1 times 2 plus 0 times 4 plus 0 times 8 plus 1 times 16. Well, that's 1 plus 2 plus 16. That's the number 19 in decimal. So we have a method for going between binary numbers, like this, and decimal numbers. Of course, this could also be a decimal number. This could be 10,011, which is a perfectly fine number. So to tell you that this is binary, I'm going to put a little 2 down here. And to tell you that this is decimal, I'm going to put a little 10 down here. Or sometimes I'll just put a decimal point. The 10 is more clear. And so we can represent numbers in different bases or different radixes. So we could think of this as radix 2. And radix just means, you know, we're using powers of 2. We can think of this as radix 10, which means we're using different powers of 10. 9 times 1 plus 10 times 1, or 1 times 10, 10 plus 9, 19. We could work in octal. Octal is radix 8, sometimes called base 8. And when we write a number in octal, like 101 base 8, what does that mean? Well, this first digit is the ones position. This is the eighths. This is the 8 squared, which is 64. And so this number is 1 times 1 plus 0 times 8 plus 1 times 64, which is 65 decimal. So in octal, or in base 8 or radix 8, 101 corresponds to the decimal number 65. And we can work in pretty much any base that we want. We can work in base 3, we can work in base 7. Most often we're going to work in binary, base 2, octal, base 8, decimal, which is base 10, or hexadecimal, which is base 16. And so base 16, if you have, you know, a 4-digit number, this is the ones place, this is the 16th place, this is the 256th place, and this is the 4096th place, 16 cubed. And so if I write a number like, you know, 3, 4, 5, 6 in octal, and we can write a little 16, or sometimes we'll put an X down there. This is equal to 6 times 1 plus 5 times 16 plus 4 times 16 squared plus 3 times 16 cubed. But the trick with hexadecimal is, you know, each of these digits could be anything from 0 to 15. And if I write a 15 right here, how do I know that that's 15 in the ones place, as opposed to a 5 in the ones place and a 1 in the 16th place? So we use different symbols. So 0 through 9 we just write as 0 through 9, but 10 through 15 we write with the letters A, B, C, D, E, F. So if I were to write the number FFFF in hex, that's 15 plus 15 times 16 plus 15 times 16 squared plus 15 times 16 cubed. Hexadecimal is nice, though, because it breaks our binary numbers into groups of 4. And it turns out if I write a binary number like this, there's a 20-bit number. If I want to write this in hexadecimal, all I have to do is break it into chunks of 4 bits each and write down the hex digit corresponding to each of those 4 chunks. 7, 1, 5, 0, 9. This number in binary is the same as this number in hexadecimal. Alright, we are running out of time way too fast here. We've only got about 4 or 5 minutes left. And I wanted you to get started on the homework. So there's a thing on Canvas, a guide to writing up homework. Take a look at that and ask me if you have questions. But basically, I just want you to do your homework neatly. I want you to work from top to bottom. I want to be able to follow your work. Right? Most important thing is I should not just see the correct answer, but I want to see the steps that got you there. Because if your answer is incorrect, but your steps are mostly correct, you'll mostly get full credit. Right? If the answer is incorrect and there's no work, then you really can't get much of any credit. So you want to show me how you got to your answer, which means work neatly, go from the top to the bottom, circle your answers, make sure the number of the question is on the side of the page, make sure you do your questions in order, and so on and so forth. So you can read the guide to homework for specifics. As far as the homework itself, the homework sets are generally broken into 2 sets of problems, solved and unsolved. And my suggestion is don't look at the solved problems. Go straight to the unsolved problems and try to work those out. Go through your notes, come to office hours, come to lab hours and ask questions in class, go through the textbook, watch the videos and so on. If you can't figure out how to do these, then you can take a peek at the solved version. Maybe take a look at the solution for part A up here and see what happened. And then come down and try to do the unsolved problems. And if you're still stuck, maybe take another look at the solved problem. Right? And if it's not making sense, come by office hours or ask questions or something like that. So you're responsible for doing the unsolved problems. You don't have to do the solved ones because the solutions are already here. But you should write up the unsolved problems. And some of the assignments on Canvas will say, do these questions only. So make sure you read what Canvas says. So for homework 1, right, you want to do the unsolved problems from this first set. And there's questions about, converting numbers from binary to hexadecimal. Converting numbers from binary to octal, which means break them into groups of 3. We did not get to negative numbers yet, so convert from octal and hex to binary. Convert to their decimal equivalents, so multiply these by powers of 8 or 16 or 2 and so on. So we have not gone through 2's complement yet, so you'll have to hold off on question 5 until next week. Negative numbers, we'll have to hold off on that one. Number of bits required to represent artwork. So if you make a truth table and you have, say, 3 input variables, right? We said that there's 8 rows in that truth table. Why is it 8? It's 2 to the 3rd. So suppose you were using a set of bits to represent, one of 2,520 art pieces. This question is, how many bits do you need? So is 1 bit enough? No, because with 1 bit you can only represent 2 things. Is 2 bits enough? No, because with 2 bits you can only represent 4 things. You could use 0, 0, 0, 1, 1, 0, or 1, 1. So for n bits, you can represent 2 to the n different things. And so if you want to represent 2,520 different things, how many bits do you need? So it's just asking kind of the reverse direction of if you have n bits, how many things can you represent? If you want to represent this many things, how many bits do you need? So think about that. And then question 9, we're going to have to hold off until next week. We'll talk about analog to digital conversion on Monday. So you should be able to do all of this homework except the 2 question on 2's complement and the question on A to D conversion. We'll go through those on Monday, and then those should be pretty quick to write up. All right, we are totally out of time. So I will leave it there. Come by lab hours tonight in this same Zoom room if you want to talk about lab or homework questions, or come by office hours. Otherwise, I will see you on the next class. All right, thank you very much.
Thank you.